Welcome back to the Explainer. Let's crack the code of geometry. Today, we're embarking on a fascinating detective's journey to uncover the hidden rules of scale. If you've ever wondered how things grow or shrink without losing their core identity, well, you're already thinking like a master mathematician. We're going to build complete conceptual mastery of triangles right from the ground up. So to kick things off, let's look at a totally relatable mystery. If you shrink a photo on your phone, how does the math know not to distort the image? Think about it. When you pinch your screen to zoom out, the picture gets smaller, right? But nobody's face gets weirdly wide and the buildings don't look squashed. How does your phone know exactly how to preserve reality? It's definitely not magic. It's actually pure foundational geometry at work. And the answer lies entirely in the mathematical rules of similarity. Which brings us to part 1, the shapeshifter's secret. Take a look at these two pictures of the Taj Mahal. They are what we call mathematically similar. The computer, or in real life, the architect, utilizes a precise scale factor, also known as a representative fraction, to resize the image without any distortion. Just look at those towering minarets and that massive central dome. In the smaller image on the right, literally every single pixel has been reduced by the exact same mathematical ratio as the image on the left. The ratio of the corresponding sides, like the height compared to the width, remains perfectly locked in place. This is the exact same scale factor concept architects use when they draw up blueprints for a massive skyscraper. Now this is absolutely crucial, probably the most important distinction for your geometry toolkit. Congruent figures are your identical twins. They have the same shape and the exact same size. If you place two identical textbook pages on top of each other, they match perfectly. But similar figures, they have the same shape but different sizes. They're like a real life-size building compared to its miniature blueprint. So remember, all congruent figures are similar, but similar figures absolutely do not need to be congruent. Okay, moving on to part 2, rules of the polygon. Let's see how this plays out with basic shapes. Notice how all circles, regardless of their radius, naturally share the exact same shape. Because of this, they are universally similar. You could have a tiny circle the size of a coin, or a massive circle the size of a planet. Because a circle is defined simply by a constant distance from a center point, there's literally no way to distort its shape. Every single circle in the universe is mathematically similar to every other circle. And this exact same natural law applies to squares. Think about their structure. Their angles are completely locked at 90 degrees, and their sides are all equal. Because of that, every square is always similar to any other square. You can't draw a square with a different angle, right? Because the internal structure is locked at those 4 90-degree corners, stretching one side means you're forced to stretch all the others equally just to keep it a perfect square. Let's build on that and look at equilateral triangles. They also effortlessly maintain similarity, no matter how much you scale them up or scale them down. Just like squares, an equilateral triangle is totally locked by its nature. All 3 sides are equal, and all 3 internal angles are exactly 60 degrees, always. So circles, squares, and equilateral triangles, those are the easy ones. They are basically born as similar. But what happens when we look at more complicated shapes? For that, we need some ground rules. For any 2 complex polygons to be declared similar, they must pass a really strict 2-part test. First, all their corresponding angles must be equal. And second, all their corresponding sides must be in the exact same ratio. Oh, and obviously they need the same number of sides to begin with. You can't just have one or the other. Think of it kind of like baking a cake. The angles give you the flavor profile. They tell you exactly how the sides lean into each other. But the sides, they give you the portion size. If you double the length of one side, you have to double the length of all the corresponding sides. If the angles match perfectly and the sides share the exact same scale factor, boom, you have mathematically similar polygons.
All right, let's test this out in part 3, the triangle lab experiment.
I want you to grab a mental pencil and walk through these precise steps with me. This is a brilliant way to see how parallel lines slice across an angle. Step 1. Draw a big open angle, and let's call it XAY. Step 2. Take a ruler and make 5 perfectly equally spaced marks along the bottom arm, AX. Let's call them points 1, 2, D, 4, and B. Step 3. Close the triangle by drawing a line from point B up to the top arm, AY, and we'll label that intersection C. Finally, step 4. The magic step. We draw a line from one of our spaced points, let's use point D, that is perfectly parallel to that closing line BC, and it intersects the top arm at point E. Now, When you actually draw this out on a whiteboard, you create a smaller triangle ADE, nesting perfectly inside a larger triangle ABC. By drawing that parallel line DE, we've essentially sliced the big triangle. But we didn't just chop it randomly. That parallel line acts as a strict geometric rule, forcing the top arm of the angle to behave exactly like the bottom arm.
Let's look at the numbers. Because we deliberately spaced our points on the bottom arm, we can literally count that the ratio of segment AD to DB is precisely 3/2. And incredibly, if we measure the top arm, the ratio of AE to EC gives us the exact same fraction. Let's break down why that's so cool. On the bottom arm, from A to D, we count 3 spaces. From D to B, we count 2 spaces, ratio 3:2. Now, if you take a physical ruler, measure the distance from A to E, and then E to C, and divide them, you get the exact same mathematical value, 3/2. The parallel line perfectly transfers the proportion from one side of the triangle right over to the other.
Which leads us perfectly into part 4, Thales' brilliant theorem.
That incredible alignment of ratios we just saw, totally not a coincidence. We owe this foundational discovery to Thales, a brilliant Greek mathematician from over 2,500 years ago. He's the detective who figured out the underlying mechanics of proportional geometry. Thales looked at the world, saw these relationships, and realized they weren't just random chance.
He gave us theorem 6.1, widely known as the basic proportionality theorem. It states, if a line is drawn parallel to one side of a triangle to intersect the other 2 sides in distinct points, the other 2 sides are divided in the same ratio. Basically, parallel lines are the magical instruments that force triangles to scale proportionally. Let that sink in for a second. It doesn't matter how long or skinny or wide the triangle is. If you shoot a parallel line through it, you are guaranteed to split the 2 sides it crosses into the exact same proportions. It is a literal cosmic rule of mathematics. And for us, the crucial takeaway is this massively powerful algebraic equation. AD over DB equals AE over EC. Anytime you see that parallel line inside a triangle, you can instantly set up this perfect balancing ratio to solve for missing measurements. If you know 3 of these pieces, you can easily use basic algebra to find the 4th. This equation is your master key. It's like a perfectly balanced scale. Whatever happens proportionally to the left side absolutely must happen proportionally to the right side. Now for part 5, the AA shortcut. So measuring every single side and angle to prove that 2 triangles are similar sounds totally exhausting, right? Luckily, we don't actually need to verify all 6 pairs of corresponding parts to know they are perfectly similar. If we put 2 varying triangles side by side, we can use a massive shortcut for our mathematical toolkit. And that is the angle, or AAA similarity criterion. It tells us that if corresponding angles are equal, the sides will naturally fall into the same ratio. If you simply prove the 3 angles match, the math guarantees the sides will automatically be locked into that perfect scale factor. You don't even need to measure the lengths. The angles are basically the DNA of the triangle. If the internal angles of the first triangle match the internal angles of the second, those 2 triangles are definitively similar. Their sides have literally no choice but to be proportional. So as we wrap up this explainer, I want to leave you with a real-world puzzle. Knowing that shadows create parallel rays of light, how could you use Thales' theorem and a simple stick to calculate the exact height of a massive mountain without ever actually climbing it? You now have the conceptual mastery of similarity to unlock the actual measurements of the physical world around you. By understanding the basic proportionality theorem and the AAA shortcut, you aren't just pushing numbers around on a page anymore. You have the tools to measure the unmeasurable. Keep observing, keep questioning, and remember that the rules of geometry are all around you.
Hey everyone, welcome to this explainer. Have you ever felt totally bogged down trying to memorize a massive, never-ending list of textbook geometry rules? Yeah, me too. Well, you are in the exact right place. Today, we aren't just blindly memorizing. We're going to build complete conceptual mastery from the ground up. Let's roll up our sleeves and see exactly why triangles behave the way they do.
Here is our roadmap for today. We'll start with shadows and shapes, uncover the AAA shortcut, explore the SSS proportionality rule, find the SAS golden middle, and then pack up your ultimate similarity toolkit. All right, section 1, shadows and shapes. This is our light bulb moment. Before we even look at a single number, let's anchor this math in the real world. Picture this. You're holding a flat piece of cardboard directly under a bright ceiling light bulb, casting a shadow right down onto your desk. Now, because light travels in straight lines, that shadow, it's an exact magnification of the cardboard.
The shape is completely identical, right? But the size has blown up. This is absolutely brilliant because it perfectly illustrates our core concept. Similar figures have the exact same shape, just different sizes. Now here's the catch. The formal textbook definition of similar triangles says two things absolutely must be true. First, all three corresponding angles have to be equal, and all three corresponding sides must be in the exact same ratio. Think about that for a second. That means you have to verify 6 different parameters. So the million-dollar question for us is, do we seriously need to do all that heavy lifting every single time, or is there a mathematical shortcut? That brings us to section 2, the AA similarity shortcut, or angle, angle, angle. Let's uncover our first major discovery. Grab a mental protractor and let's walk through activity 4 from the textbook together. Imagine drawing a baseline segment, and at the ends, you lock in 2 very specific angles, let's say 60 degrees on the left and 40 degrees on the right. Now, do that exact same thing on a much longer line segment. Here's where the magic of geometry kicks in. Because of the angle sum property of triangles, that third angle up top, it automatically locks into place to hit exactly 180 degrees. Boom. You've just built 2 triangles with completely identical angles. But wait, it gets better. Notice what happens when you swap that protractor for a ruler. If you measure the lengths of the sides on both of these new triangles and then divide the smaller sides by their corresponding larger sides, the ratios of all 3 sides magically pop out to equal exactly 0.6, or 3/5. There's no way around it, it happens every single time. Just by locking in those angles, the sides literally have no choice but to fall into perfect proportion. And guys, this is our first massive shortcut, Theorem 6.3, the angle, 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 or simply AAA criterion. It basically tells us, hey, if you can just prove the corresponding angles are equal, the side ratios are 100% guaranteed to match. You don't even have to measure them. In fact, since the third angle is always forced by the first 2, you technically only need to check 2 angles. That's the AA shortcut. Moving right along to section 3, the SSS proportionality rule. Side, side, side. Okay, so we just saw that locking the angles forces the sides to behave. Well, what if we flip the script completely? Let's mentally sketch out activity 5. Toss the protractor this time and just grab a ruler. We're going to intentionally draft 2 triangles where the sides are strictly proportional. First, draw a triangle with sides measuring exactly 3, 6, and 8 centimeters. Next, draw a second triangle where every single side is exactly 1.5 times longer, so 4.5, 9, and 12 centimeters. The ratio of the corresponding sides here is perfectly locked at 2:3. So what you've essentially done is built a rigid cage of proportional sides. Now what do you think happens when you drop your protractor onto the corners of these newly drawn triangles? Incredible as it seems, angle A perfectly matches angle D. Angle B matches angle E. The proportional sides automatically locked those interior angles into the exact same degrees. Isn't that wild? And just like that, you've conceptually proven Theorem 6.4, the SSS, or side-side-side similarity criterion. It proves that if those 3 side ratios match up, the angles have absolutely no choice but to be perfectly equal. One condition completely dictates the other. Boom! You just cut your geometry workload in half again. All right, section 4, the SAS golden middle, which stands for side angle side. So we've checked all the angles and we've checked all the sides, but is there like a golden middle ground? Let's visualize activity 6. Sketch out 2 triangles, but this time lock in only one angle. Let's make it 50 degrees. Now, make sure that only the 2 lines branching out from that corner, the sides embracing that angle, are proportional. Let's say 2 and 4 centimeters on the small triangle and 3 and 6 centimeters on the larger one. We are completely ignoring the third side and the other 2 angles for a second. Now, grab your pencil and connect the endpoints to form that third side. What happens? That remaining side effortlessly snaps into the exact same 2/3 proportion as the others. And you guessed it, the remaining angles perfectly align as well. This right here is Theorem 6.5, the SAS, or side angle side criterion. It brilliantly proves that if just one angle matches and the sides hugging it are proportional, the entire triangle is similar. We literally only needed a fraction of the info to solve the whole puzzle. Finally, section 5, your similarity toolkit. Time to master these triangles. Now it's time to organize all these awesome discoveries into a powerful toolkit for your exams. To sum it all up,
You never ever have to check all 6 parameters again. If you see corresponding angles match, shout AAA. If you see all sides are proportional, shout SSS. And if you spot a locked angle hugged by proportional sides, you've got SAS. The core rule here is beautifully simple. In the world of triangles, one condition implies the other. And hey, remember how the textbook actually proves these theorems mathematically? It doesn't just use abstract, boring algebra. It uses tactile, physical math. The proofs literally involved marking points on the larger triangle, cutting out a piece perfectly identical to the smaller triangle, and superimposing it directly inside the larger one. They use parallel lines to prove everything perfectly aligns. It's such an incredibly visual and logical way to see the math physically locking into place. I want to leave you all with one final provocative thought today. Geometry isn't just ink on a textbook page, it literally governs the physical space you exist in right now. So take a second and look around your room. Seriously, look around. Find the math hiding in plain sight. Which objects around you are similar, perfect magnifications of each other, and which are completely congruent, identical clones? Keep an eye out for those ratios, and I will catch you in the next explainer. All right, let's get right into it. Welcome to a very special explainer. Today, we're literally going behind closed doors. Now, if you're a 10th standard student gearing up for those highly competitive Karnataka SSLC board exams, I already know you've got the basics down. You know what a triangle is. You know your definitions. So we aren't going to sit here and waste time reteaching the textbook. Instead, we're tackling Chapter 6 triangles from a totally different angle, the evaluator's perspective. We're going to completely decode the official model answer keys and the board's evaluation schemes to see exactly where students bleed marks and, more importantly, how you can maximize your score. Consider this your masterclass in playing the exam game perfectly. Here is our official evaluator's blueprint for today. We'll quickly run through. Section 1, securing 1-mark quick hits. Then, Section 2, cracking the BPT proof. Section 3, scoring similarity criteria. Section 4, Pythagoras application traps. And we'll wrap up with Section 5, the final exam master strategy. Let's do this. Kicking things off with Section 1, securing 1-mark quick hits. These are your guaranteed points. Okay, these are the absolute favorite questions examiners use to test your foundational knowledge when you're under time pressure. Check out this exact instruction pulled straight from the official SSLC evaluator key. It literally says, give full marks for direct answer. Evaluators are explicitly told that for these 1-mark multiple choice or short answer questions, they do not want to see lengthy multi-step calculations. If you know it, just state it clearly. You get the full point instantly. No fluff needed. Here's exactly what I mean by a quick hit. Take a look at the 2 triangles presented here. You've got sides measuring 2, 2.5 and 3 on the left, and 4, 5, and 6 on the right. Now, recognizing instantly that 2 is half of 4, 3 is half of 6, and 2.5 is half of 5 means the sides are perfectly proportional. Boom. You just write down SSS, or side-side-side similarity criterion. That's it. That is the exact keyword the examiner is hunting for to award that direct 1-mark hit. No massive essays required whatsoever. Another guaranteed point area, theorem statements. You have to memorize them word for word. Look at the official phrasing for the basic proportionality theorem, also known as Thales Theorem. If the exam asks you to state it, do not try to paraphrase it in your own words. Write exactly this text. If a straight line is drawn parallel to a side of a triangle, then it divides the other 2 sides proportionally. Nailing that precision is a non-negotiable 1-mark guarantee. Moving right along to Section 2, cracking the BPT proof. Let's look at the anatomy of a 4-mark answer. Now we're escalating to the heavyweight 4-mark giants, starting with that basic proportionality theorem. Before you even think about writing a single equation, take a look at the official BPT evaluation diagram. Do you see the dotted lines used for construction, the tiny perpendicular markers? Simply drawing this accurately with a pencil and ruler gets you on the scoreboard before any actual math happens. Let's actually break down that rigid scoring rubric, because this is the exact step-by-step point allocation the board uses. Step 1. Just drawing the figure secures a half mark. Step 2, clearly writing out data and to prove under separate headings, you just earned a full 1 mark. Step 3, writing down your construction steps gets you another half mark. Guys, notice that before you even start the complex mathematical proof in Step 4, you have already secured 2 out of the 4 marks. Presentation is quite literally half the battle here. But here is exactly where students bleed points. A super common mistake is rushing straight to the final proportional ratios. Evaluators are setting a massive mark trap right here. The evaluator's expectation, what they're actively scanning your paper to find, is the explicit use of the triangle area formula. You absolutely must write out that the area of the triangle equals half base times height. For example, explicitly writing area of triangle EDE equals half times AD times EN, and then physically showing the ratio of those areas. If you skip this area step because you're rushing, you are going to forfeit crucial partial marks. All right, Section 3, Scoring Similarity Criteria. Let's avoid the traps. This is an area where students constantly fall into traps just by being a little too casual with their definitions, mixing up angles and sides. Read this SAS similarity criterion carefully. It says, if one angle of a triangle is equal to one angle of the other, and the sides including these angles are proportional, they are similar. That specific phrase right there, sides including these angles, is the exact keyword sequence evaluators are trained to look for. If you just write that two sides are proportional and an angle is equal, but you completely forget to specify that the angle is included between those specific sides, you're going to lose the mark. In geometry, precision is your best friend. And hey, if you're ever worried about which method to use for proofs like AAA or SAS similarity, this direct quote from the evaluator's instructions should be a massive relief. It literally says, if the theorem is proved as given in the textbook, give full marks. So don't overcomplicate things. Don't try to use advanced alternative proofs you found somewhere online. Stick strictly to the standard method outlined in your KTBS textbook, and the board promises you 0 deducted marks. Let's pivot to Section 4, Pythagoras application traps. It's time to scavenge some partial marks. So when you're facing down those long-form 3 or 4-mark application questions, it's really not just about getting the final answer perfectly right. It's about scavenging every single partial mark along the way. Look at this actual board evaluation scorecard for a complex Pythagoras problem. Notice that right-hand column? See all those half fractions stacked up? Evaluators don't just look at the bottom line. They award marks incrementally for every correct logical step you put on the paper. Let's completely decode that scorecard. Look at how a 4-mark question gets scavenged step by step. Step 1, just stating the 2 initial right triangle Pythagoras equations gets you a half mark for each one. Step 2, showing the algebraic subtraction of those equations gets you another half mark. Step 3, substituting the given values, yep, another one. Think about it. Even if you completely mess up the final simplification in Step 4 because of exam panic, you've already secured 2.5 or 3 marks just by documenting your algebra clearly. Every single step is a checkpoint. Treat it like one. So if you take nothing else away from this masterclass, remember this number right here, 1/2. For almost any 3 or 4-mark geometry question, simply drawing the figure correctly with a ruler based on the question prompt earns an automatic half mark. I don't care if the math totally blanks from your mind, never, ever leave a geometry question entirely blank. Draw the figure, take the free half mark. Which brings us to Section 5, the final exam master strategy. This is your battle plan. Let's pull all these evaluator secrets together into an actionable, high-yield checklist for exam day. Lock this into your brain. Number 1, never skip the diagram. It's an automatic half mark. 2, always structure your proofs with separate, clear headings for data, to prove, and construction to easily secure presentation points. 3, don't just say the triangles are similar. State the exact criterion, like AAA or SAS. 4, in the BPT proof, explicitly show those area ratio formulas. No skipping steps. And 5, when proving theorems, stick strictly to the textbook method to guarantee full credit. Whatever you do not leak marks because of messy presentation. I want to leave you with this final thought. You've studied the textbook, you understand Chapter 6, you know the math, but ask yourself, how are you actually presenting it? Are you rushing the steps and leaving guaranteed half marks on the table for the evaluator to just swipe away? Use this blueprint. Format your answers exactly the way the board wants to see them, and go claim every single mark you deserve. Good luck out there.